Alrighty, so today we are going to discuss a new technique for analyzing circuits. Previously, of course, we have Ohm's law. Ohm's law is the main fundamental relationship between the current, the voltage, and the resistance in a circuit. And in general, given a circuit, if you're able to deduce whether the resistors are connected in series or parallel or some combination, you can use Ohm's law to figure out a lot of information about the circuit, the current running through the circuit, how much voltage is dropped by each resistor, and so forth. However, not all circuits can be analyzed using Ohm's law. A lot of times, circuits are more complicated. Some of the resistors may not be connected in either series or parallel, or you may have multiple voltage sources, or any combination of things can happen to where if you tried to use Ohm's law, you'd get stuck and you wouldn't be able to proceed. And so for the rest of the semester, of course, we're going to learn a bunch of different techniques to help handle this issue. Unfortunately, there is no single technique which can be used to solve every single circuit. So we need to learn a whole bunch of different techniques and build up a tool chest with a bunch of techniques that we can pull out and use for any given circuit. But we can't rely on just one thing. However, loop analysis, which is what we're going to discuss today, is pretty powerful and can be used to solve a great number of circuits. Usually, loop analysis is taught alongside a second technique called Nodal Analysis. But of course, I'm going to split them up into two different lectures and concentrate on each one separately. But they're very similar in how to attack the circuit. The difference being, one uses the voltage, or you're able to calculate the voltage, let's say, dropped by a particular resistor, making use of the current flowing through the circuit, whereas the other is the exact opposite. By learning about how much voltage is there, you can calculate the currents. So let's discuss loop analysis. In order to do loop analysis, you're basically going to have a circuit. Let's say you have a circuit, something like this. And this time what I'm going to do is I'm going to put multiple voltage sources in. And so maybe we'll let this be V1, this will be V2, this will be R1, R2, and R3. And so right off the top, we can tell trying to use Ohm's law is going to be pretty difficult here because we've never seen how to work with a circuit which has multiple voltage sources. But you'll find that in loop analysis type problems, this comes up a lot. Not always. You can do loop analysis even if you don't have multiple voltage sources. But when you see multiple voltage sources, it's a hint that, hey, you may want to try this. So what does this technique do? Well, it makes use of a major rule, and the rule is this. We kind of discussed it previously. The rule is that the total voltage along a closed loop must be 0. And we saw this when we discussed Ohm's law. I had said, if you have multiple resistors in a circuit and you have a voltage source of, let's say, 10 volts, then you know that once you've added up how much voltage is dropped by each resistor, they better add up to the total of 10 volts. So if you have 10 volts to use, you're going to use all 10 volts. Well, now we're just describing this a little bit more specifically, and it not only holds for the whole circuit, but it holds for any what's called closed loop of a circuit. And so imagine with this particular example I have, let's say I allow this left loop, so going around this way, there's going to be some current flowing. I'll call it I1. And we're just going to pretend like it only lives in this left square. It moves around the wire. It doesn't go over here to this side. It just lives in this left loop. What this rule says is that if I add up all the voltages along this path, they better add up to 0. How does that happen? Well, let's see. Let's follow the loop, follow the current. The current, let's say, leaves the voltage source. Well, first of all, I started at the voltage source, so I have some voltage to start with, V1. Then what happens? The current leaves, hits R1. What happens when a current and a resistance gets together? I times R gives you a V. So, when this current I1 hits this resistor R1, some of this voltage is dropped. It's used up by the resistor. So if it's dropped, that means we're going to subtract it away from what was there before. Thus, we started with V1. Our current hits R1, so we drop some amount of voltage. How much voltage do we drop? Well, of course, we drop I times R. That is, let's call it like a VA. So right here for resistor 1, there's some voltage A that's dropped. What is that voltage A? It's the current that hits the resistor times the resistance of the resistor. Now we keep going. We now leave resistor 1. We move around. We are keeping going along this left loop, and then all of a sudden the current hits R2. Well, again, here's a current hitting a resistor that's going to give rise to a loss of voltage. How much? Well, let's say it loses some amount called VB. What is this VB? Well, it's the current that hits the resistor, I1, times the resistance of that resistor. In this case, it's R2. That's the thing I'm calling VB. Now, VA and VB, that's just labels. It's immaterial. It doesn't matter. But just so you see what I times R represents, it represents an amount of voltage that was lost by that resistor. All right, then what happens? We leave R2, we continue on, and we get back to the beginning again. So we've gone around one whole closed loop. I add up all the terms, and I better get 0. That's what the rule says. And now we see. Here's an equation. This equation is an equation of voltages. You started with V1, you lost some V at R1, and you lost some V at R2. How much did you lose? I times R. We don't know what I is. We just made up the fact that there's some I1 flowing around in this circuit. There must be. We don't know what the value is. We eventually want to figure out what this value is. So for now, we're just calling it I1. Later on, we're going to figure out how much that is. So we started with V1. Then our I1 hits this first resistor, so we lose voltage, so it's minus I1 times R1. And then we continue along, keep going on our little closed loop. I1 hits R2, so again we lose voltage, minus I1 times R2 is the amount we lost. And we keep going and we get back to the beginning, set it equal to 0, and we have our first equation. Pretty nice. What about the second loop? There's two loops in this problem. We better worry about this. So, again, I'm going to pretend like there's some current flowing in this second loop. It's not necessarily the same as the first current. There's no reason it has to be the same number. So I'll call it I2. And now we want to do the same thing we did before. We're going to go along our little loop in the direction I've chosen. I've chosen it to be clockwise. That was an arbitrary choice. It could be counterclockwise. I don't know. But since I don't know, I have to guess one. And it turns out later on, if I happen to guess the wrong way, if the current is actually flowing the other way, when I solve for the current, I'd get a negative number. So I know, oh, it was going the other way. It's no big deal. You're allowed to guess one way or the other, and you must. Generally, what you're going to find is I'm always going to guess clockwise. That's not always efficient. Sometimes using information by looking at the circuit to tell you which way the current will flow is better, and then you'll never get a negative. But just to not have to worry about trying to guess or trying to figure it out, just always make it clockwise. If you get a negative answer, that's perfectly fine. All right, so let's look at the second equation. Our yellow arrows are for that loop. Look at this top yellow arrow. It's moving along, and the first thing it does is it hits the voltage source V2. Now, usually that would mean, okay, here's a source of voltage. We're going to gain this much voltage. But there's a problem. Notice which way the arrow's pointing. For the green loop, the arrow was pointing out of the longer line and going around, and it comes into the shorter line. Okay, so that gave us a directionality at the voltage source, which was this way, from small to big, if you look at the little symbol. But if you look on our right loop, the arrow is coming into the big loop and out of the small, so this gives us a directionality of this way on that source, which is the opposite direction. What this means is instead of gaining a certain amount of voltage, you're losing a certain amount of voltage because of this source. And it's purely because you chose the current to flow in this direction, and this direction for this voltage source makes it a negative voltage. So just remember this rule. If the current goes from small to big on the voltage source, you're positive voltage. If it goes from big to small, it's negative voltage. And when I say small to big and big to small, what I mean is this symbol for the voltage source. If the current comes this way, it's hitting the small side, then the big side. That's a positive voltage. If instead, the current was coming this way, it hit the big side first, then the small side, that's a negative voltage. Okay? So with that in mind, we look at this second loop. There's I2 coming along, hits the voltage source, but hits it backwards, big, then small, so we lose minus a voltage. How much do we lose? The source, V2, whatever it is. Then we continue along, and then our yellow arrows hit R3. So here's I2, the second current, is now hitting R3. Every time this happens, we lose a certain amount of voltage. So we're going to lose. How much do we lose? The current that hits the resistor, I2, times the resistance, R3. And then we continue, we leave the resistor, we go up the middle line there, and then we're back at the beginning again. So that's the whole closed loop, just these two things. So we set it equal to 0. And we have a second equation. What is it we're solving for? In this case, we're going to know V and we're going to know R. So what we're solving for are these I's. We're going to want I1 and we're going to want I2. Those are going to be our unknowns in a real problem. Now, in this case, it's okay. The first equation just has I1 in it, so we would solve it just like a regular equation. And the second equation just has I2, and so we would solve it like a regular equation. No big deal. However, in other examples, we're going to find that I1 and I2 mix in the same equations. And so what we're going to wind up having is two equations, two unknowns type things. Okay, we'll see that, but just note, normally that's what's going to happen. You're not just going to have two easy equations to solve independently. You're going to be left with two equations with two unknowns that you have to solve. Or if we have three loops, then we'd have three equations with three unknowns. And so we'd have to do the algebra to try to figure those equations out. So that's it. That's everything. That's loop analysis. So let's look at an example. Let's try one out. Example. All right. Here's a circuit. All right. What do I want to solve for? Let's say I'd like to solve what is the current flowing through the 2 ohm resistor and what is the current flowing through the 4 ohm resistor. Or I can even do like we did before, and we could say, here's a table, R, I, V, and for each resistor, we want to solve these things. This will be even easier. Just find everything. Okay, for each one of the resistors, I want to know how much current is hitting that resistor and what's the voltage drop by that resistor. Just like we did with Ohm's law, only now we're going to use loop analysis to do it. All right, so what's the process? First thing, if I know we're doing loop analysis, perfect. If I don't, I'm looking at this circuit. I see there's two voltage sources. I'm going to use loop analysis. So first thing I do is each loop in my circuit, I'm going to create a current flowing in some direction. In this case, I'm going to choose in this left loop, there's a current flowing clockwise. Oops. I'll call him I1. And in the second loop, I'll also do clockwise, and I'll call him I2. Once I know this, the next step is to create an equation for each loop. The equation consists of the sum of all the voltages. Of course, some are going to be negative because they're voltage drops, but we add up all the voltages on each loop and set it equal to 0. So let's look at this left loop. We'll do that one first. I'll draw the little lines. Usually I'm not going to do this, but just since this is our first example with real numbers, I'll show what it looks like. Green will be for the left loop, yellow I'll do for the right loop. So the current, here's the current starting out at the voltage source. That current hits the 10 volt source, and it hits it from the small side to the big side. That's positive. So we're going to have a gain of 10 volts. Then the current leaves. Then the current's going to hit this 2 ohm resistor. So we're going to lose some voltage. How much do we lose? I times R. What I hits that to? I1. I1 hits a resistor whose resistance, is 2. Okay. Then we leave that resistor we stay in this left hand loop, and then we hit this next resistor of 3. We're hitting a resistor with a current, so we're going to lose more voltage. How much do we lose? I times R. I1 times R. We leave that resistor, and we wind up at the beginning again. So at that point, we set it equal to 0, and that equation is done. Well, we could go ahead and solve this already if we'd like, because when I look at this circuit, what do I see? I mean, this equation, I'm sorry. I see that this equation only has one unknown in it, so this is solvable. So we have 10, and then I have minus 2I1 minus 3I1 is minus 5I1. All right, keep the I1 on one side, all the numbers on the other. So I have 5 times I1 equals 10. Thus, I1 equals 2. So I now know the current 1 flowing through the left-hand loop. Does that give me any answers? It sure does. Notice for my table, what I want is for resistor 2, I'd like to know what current hits that resistor. Well, I know what current hits it. I1 hits it. And I just calculated what I1 is. It's 2, so 2. What about the voltage? Do I know the voltage? Of course, the voltage dropped by R2 is I times R. I that hits him is 2. His R is 2. 2 times 2 is 4. All right, do I know 4, the stuff for 4? No, I don't know the stuff for 4 yet, but I do know the stuff for 3, because notice, again, the only current that hits 3 is this I1. So, resistor 3 has the same current of I1, which is 2. And then the voltage drop by resistor 3 is I times R. 2 times 3 is 6. So, that's as far as I can go with the left loop. Now we're going to look at the right loop. The right loop, we're going to do the same thing. Now I'm using yellow, so we're going to have, we start here, then I2 hits the resistor of 4. So the first thing is current hitting a resistor. We drop a certain amount of voltage, so we're going to drop how much? I times R, 4 times I2. Then we continue. We leave the resistor, then we hit a voltage source. Notice that we hit the voltage source from small to big. Small to big is positive, so we're going to gain voltage. So we're going to gain how much? The voltage of 5. So we get plus 5. Then we leave, we continue along. This is just wire, and we're back at the beginning. So we set it equal to 0. I look at this equation. What do I see? Just a single unknown sitting there, I2. So let's solve for it. 4I2 equals 5. So I2 is 5 over 4. All right. I2 is 5 over 4. What does that tell me? The current which hits resistor 4, the only current that hits him is this I2. So for resistor 4, we have a current of 5 over 4. Then what's the voltage? The voltage dropped is I times R. 4 times 5 over 4 is 5. And voila, I've got my answer. I've now filled out the table. I figured out how much current flows through each resistor and how much voltage is dropped by each. This is the heart of loop analysis. This is, of course, the basics. We're going to have slightly more complicated circuits where the algebra at the end is going to be a little bit harder. But this method, these steps, that's what's important right now. If you know when to put a negative voltage or a positive voltage, you're perfect. Now what I want to do is one last equation or example, but this time we'll do one where it gets a little more complicated. Let's look at this circuit. All right, so 10, 5, 2, 3, 4. All right, so what do I want to solve? I want to solve this table, RIV. I want to know for each resistor, what's the current drop, the current on the resistor and the voltage dropped by the resistor, just like before. What's the difference between this circuit and the last? All the numbers are the same. 2 loops, one left, one right. The difference is, notice on this first one, the 3 ohm resistor is over there on the left loop on the bottom, whereas here, it's on this middle branch. This is what's going to mix up our currents a little bit. And it's going to create equations where both unknowns are on both equations. And we'll see how to handle it. But let's go about it the same process. First thing I do, I'm going to use loop analysis here. I see 2 voltage sources. That's a good hint. Left loop, clockwise, call it I1. Right loop, I'll also do clockwise, call it I2. All right, one more time, I'm going to show the arrows of the current just to make this easier. But as we get better and more efficient, we're not going to have to draw the arrows every time. We could just picture it in our mind and just write down the equation. So, look at this left loop. What's going on here? I1 comes in from the bottom, hits the small side, then the big side. So that's a gain of voltage. How much do we gain? The voltage is 10. Then, the current continues, hits the 2 ohm resistor. So we're going to lose voltage. How much do we lose? I times R. His resistance is 2. His current is I1. Then we're going to continue and we're going to hit resistor 3. But this is where something different is going to happen. Because notice this. Let me go ahead and fill in all the arrows for both now, and you'll see why I'm doing it in a little bit. So for the right loop, we've got the arrow hitting the 4 like this over here, hits the voltage source this way, comes in, and then comes in this way. Notice, if we zoom in to resistor 3, we have one current going through downwards, and we have another current coming up from the bottom. So that is, I1 is going through resistor like that, and I2 is coming up like this. These 2 currents are moving in opposite directions. However, both currents are hitting this resistor. So the fact that both currents hit the resistor, I'm going to have to say that in this equation. I've been saying it every time, it's just for every resistor we've had so far, there's only ever been one current which hits each resistor. But now we have a resistor where 2 different currents hit. I1 hits it and I2 hits it. So, when I go to figure out how much voltage is dropped, first of all, it's negative because we're going to drop voltage. I'm going to have the resistance, which is 3. But now when I say how much current hits it, it's I1 and I2. So I have to add up the currents, I1 and I2. However, because they go in opposite directions, one of them is in the positive direction, one's in the negative direction. So instead of it being I1 plus I2, which you would think is the total current hitting it times the resistance, because they're going in opposite directions, one of them is negative. Which one do you make negative? you always make the one that's not the loop you're talking about negative. So, right now, I'm talking about loop 1. I'm on loop 1's equation, so he's always going to be the positive direction for this equation. So I2 will be the negative guy. So what current hits resistor 3? I1 and I2, but I2 is negative. Okay? So it's just like before. The voltage drop of this resistor is I times R. The difference here is the I which hits him is two different I's, I1 and I2. Usually you would add them, but you only add them if they're moving in the same direction. They're kind of combining together to get more current in that direction. If they flow in opposite directions, then they fight against each other, so they subtract. And we've made the rule that the loop you're talking about has positive current. The other loop, if it goes in the opposite direction, has negative current. So that's why it's I1 minus I2 here. But okay, done with that. We continue on. We leave resistor 3. We're now at the bottom of the loop, and we get back to the beginning, and we're done. So we set it equal to 0. And now we see a problem. Here's our equation. Everything for loop 1 in this equation. However, we have two unknowns. We've got I1 and I2. And I know from math that I cannot solve a single equation with two unknowns. So I'm going to have to make a second equation. So let's look at the second equation. Second equation is for the right side loop. Let's start at the top. The yellow arrow, I2, hits the resistor 4. I'm going to lose voltage. How much do I lose? His resistance is 4. The current which hits him, only I2 hits him, so it's I2. Then I continue on. The yellow arrow leaves 4, hits the voltage source of 5. It hits it from the top, from the large, long line to the small. Long to small is negative. You're losing voltage. So this is going to be minus the voltage source. And we continue on. We're at the bottom of the loop. There's nothing there. Then we're in the middle branch again. Okay. So there's resistor 3. Resistor 3 is going to drop some voltage. How much? Well, drop is negative. His resistance is 3. And we need to know what current hits resistor 3. Again, we just did this. Both currents hit them, so I have to add them up. However, one has to be negative because in this case, they're moving in opposite directions. This equation, we're talking about I2. So I2 will be the positive guy now, and it's I1 who's the negative. So it's going to be I2 minus I1. That's very important. A lot of people make the mistake, if they made I1 minus I2 in the first equation, they do I1 minus I2 for the second as well. But remember, each equation is separate, and the directionality is chosen for that particular loop. For the first equation, I1 was the positive direction. However, for the second equation, we're looking at the second loop, and the second loop is all about I2. So I2 will be the positive direction now. But there we go. So I times R for 3. And then I continue on. I'm back up at the top. I'm done. So I set it equal to 0. And again, I see, same problem. I2 and I1 in this equation. Two equations, two unknowns. If I can solve two equations, two unknowns, I'm going to have my answer. And I know how to solve it. That's, of course, why at the beginning of the semester we did the little math review where we discussed algebra stuff, is specifically for this reason. So let's do it. First thing I'm going to do is I'm going to take this first equation and I'm going to simplify it a little bit. I'm going to distribute everything out so we can see all the terms. We've got 10 minus 2i1 minus 3i1 plus 3i2. Notice here, there's negative times negative makes it positive. Don't make a mistake here, especially on a test when you're rushing, to forget negative times negative is positive. Okay, so everything's distributed out, set it equal to 0. I now combine terms. So let's see, I've got, I'm going to keep all the i's on the left. Well, what I'll do, I'll just do it one step at a time. 10 minus 5i1 plus 3i2 equals 0. And now I know I'm doing two equations, two unknowns, so my first step to doing it is to take one of the equations and solve for one of the unknowns. I'm going to solve this one for I1. So I get I1 is 10 plus 3i2 over 5. All right, that's as far as I could go with him. I now have to look at the second equation. Well, let's see. Again, let me distribute. So we have minus 4i2 minus 5 minus 3i2 plus 3i1. Combine all the terms. So I've got minus 5 plus 3i1 minus 7i2 equals 0. And now, here comes the two equations, two unknowns, substitution stuff. Take I1 and you plug it in for I1. What do we get? Minus 5 plus 3 times 10 plus 3i2 over 5. Okay, so there's I1 minus 7i2 equals 0. All right, well, this looks kind of messy. We have an equation sitting here. First of all, it's only got one unknown, I2, so that's good. However, it's got a fraction sitting there. I don't like that denominator. So the first thing I'm going to do is I'm going to multiply everything by 5 to get rid of that 5 in the denominator. Okay, so take this whole equation, multiply it by 5. What happens? All right, so minus 25 plus 5 times the second term, the 5's go away, so I have 3 times 10 plus 3i2. And then minus 5 times 7 is 35, i2 equals 0. All right, this is looking better. Minus 25 plus 30 plus 9i2 minus 35i2 equals 0. All right, get all the i2s on one side, all the numbers on the other. So we have 5 equals 26i2. So I2 is 5 over 26. All right, we have one of the i's. Let's get the other one. How do we get the other one? Now that we know what I2 is, we take our original I1 that we substituted, and we plug in for I2. So we have I1 equals 10 plus 3 times I2, but I2 I know is 5 over 26. All of that over 5. All right, so what do we get? Let's see. 2 plus 3 over 26, which is 55 over 26. Now, obviously, I don't have a calculator right now, If you have a calculator, you'll have decimals here. But there we go. I now know what I1 is. I1 is 55 over 26. I2 is 5 over 26. Now we can solve our problem. Let's look at our table. The table we want to fill out. I want to know I for R2. Well, what current hits R2? Here's R2. What hits him? Only I1 hits him. Thus, the current for R2 is I1. And I1 is 55 over 26. Then, I want to get his voltage, so I take his I times his R. That gives me 55 over 13. So, 2 ohm resistor done. Let's look at 4. What current hits the 4 ohm resistor? Only I2 hits him. I2 I found was 5 over 26. Thus, 5 over 26 for him. And then his V, I times R, 4 times 5 over 26 is 10 over 13. So he's done. And now for the one that's slightly more complicated, Resistor 3. Why is he more complicated? Because there are 2 different currents hitting him, I1 and I2. So when I want to know what I to put for him, I need to add up the 2 currents. But remember, the way they're drawn, they're moving in opposite directions. One is hitting him from the top, the other is hitting him from the bottom, so I have to subtract them. So, what do I get? I have I1, which is 55 over 26, minus I2, which is 5 over 26, gives me 50 over 26. Okay, so what did I do for him? I just did I1 minus I2, because that's what it is. The current which hits R3 is I1 from one way and I2 from the other. So they're both there. I have to combine them. But because they're moving in opposite directions at this resistor, I have to subtract them. So I1 minus I2, there's his current. I want his voltage, I times R, 3 times 50 over 26 gives me 150 over 26, which is, of course, we can do this. 150 over 26 is the same as 75 over 13. And there we go. Table is filled out, just like before. So, yes, this is more complicated. Why is it more complicated? The algebra necessary to finish the problem is more steps. The setup, creating our equations at the beginning, was the same. Each loop, I follow the current, and I add up all the voltages. Any voltage that comes because of a resistor, that's a negative voltage. Voltage sources will be positive if the current goes from small to big, or negative if it hits the big side then the small side. Add them all up, set it equal to 0. Any resistor which feels both currents, I have to add the 2 currents together when I multiply it times the resistance. If both currents move in the same direction, I add them, I1 plus I2. If the 2 currents move in opposite directions, like this problem, where I1 was coming from the top, but I2 was coming in from the bottom, then one of them has to be negative. The one you choose to be negative is the current that's not the equation you're talking about. Meaning, if I'm on the first equation, which is an equation for I1 stuff, then I2 will be the negative guy, if he's in the opposite direction. If I'm on the second loop, which is the loop with I2 in it, I2 will be the positive one, and I1 will be the negative one, if he's moving in the opposite direction. But again, if it's in the same direction, then they're both positive. We just add them. Set up your equations. You now have two equations with two unknowns. I solved it by substitution. If you have a faster way of solving it, go ahead and use that. That's perfectly fine. And in fact, in a future video, I'm going to show you a fancy way called Cramer's rule using matrices to solve two equations with two unknowns that I like to do better than this algebraic way. So I'll show you that. You don't have to use it. You can use any method you want as long as it's mathematically legal, of course. So you solve the two equations with two unknowns. You now have your I1 and your I2. Once you have those values, you look at your table and you fill it out. Look at what the circuit has. Follow the current around the circuit. That'll tell you what I goes with which R and so forth. All right, so that's everything you need to know about loop analysis. I will, of course, be following this video up with another video with some more examples, and also teaching you the Cramer's rule method for solving two equations with two unknowns. So look out for that. Also look out for any homework assignment that might be posted. But if you have any questions, of course, please email me. I'll be happy to help to the best of my ability. And if we need to set up a Zoom meeting or something to work some problems out, that's fine too. But until next time.